Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we were discussing about a system under constrained motion. So now we have another example, an interesting example, this time of a rope with a weight, a rope having a non-negligible weight falling under its own weight off a smooth table, right? So the problem is that of a rope sliding off a table. Okay, so a uniform inextensible rope of mass m and length a is released from rest, hanging over the edge of the smooth horizontal table, right? We need to find the rope speed. We need to find the rope speed when its displacement is x. Okay, so let us draw the setup here to understand better. So we have a table and there is a rope which is lying on the table, and the rope is here, right? And the rope is here and it is here, which is B, and what we have is we need to give some initial length of the rope which is hanging outside the table, otherwise the rope is not going to slide, right? It has to have some weight hanging outside, right? So let me call this initial weight hanging outside for the rope to be B, right? So now what we have is at t equal to 0, we put an initial condition. The rope is released from rest. So at t equal to 0, we have the velocity v is 0, right? And the rope is lowered by x equal to b. So these are my initial conditions. So at t equal to 0, the velocity v is 0 and the length of the rope is b, right? And so let's say at any given time, t, if a length x comes out, at any given time, if a length comes out, comes out of the table, we have the potential given by the following. Potential V to be given by the following. Now, first we have to introduce the concept of mass per unit length, right? So the mass per unit length is m divided by the total length a, right? So the total length of the rope is given in the problem to be a. So mass per unit length is a, and now at any given time, x of the length of the rope is hanging, so we have to multiply by x. So this is my mass, total mass of the rope which is hanging, right? And of course, since it is hanging downward, so we put the table to be the zero potential base. The table is at the potential 0. So anything which is going below the 0 is going to be negative, so we need to put a negative sign. and now it is m times g times whatever the length is going down. So the length which goes down, of course, at t equal to 0, the length which was down was b, right? And at any given time point, we have the x length, which is below the table. So we expect that the center of mass of the rope is going to be half of x. Why? Because this rope is homogeneous. The center of mass will always be at the middle point. So we have b plus x by 2, right? So we have that the center of mass is given by x by 2. Okay. So from now we have written the potential. So we can now write the total energy of the system. The total energy of the system is given by E, which is half m x dot square minus m x by a times g times b plus x by 2, right? So we have that this is the case. So E is the following. Okay, so this is my kinetic energy and this is my potential energy, which is written here above, and we put a minus sign because the rope is getting lowered. Okay, so then so this is my energy. So we can find what is this constant E using my initial condition. So at t equal to 0, we have that x is equal to b and x dot is equal to 0, right? So what we have is that we can plug all this information to find E, and we can find the relation. After finding E, we have the following relation. So x dot square is v square minus g by a times x plus 2b. Okay, so that is what we have in terms of energy conservation. Okay, so that is what we have. So x dot, well, x dot is v square. Hold on. So x dot is v square. So v square is equal to g. So this is the relation here. So v square is given by this quantity. Okay. So now the next part of the problem says, is find the displacement. Displacement at time t. Find the displacement at time t, and we have that x dot is given by n times square root n x times x plus 2b, right? Where my n is a constant, n is given by square root g over a, right? So now I want to find the displacement at any given time t. So x dot is nothing but dx dt. I can integrate this relation to find that my x is 2b sine hyperbolic square nt by 2. Okay, I've just directly integrated using my initial condition that at t equal to 0 we have x equal to 0. So that is my initial condition. So that clears the indefinite constant of integration. Okay, so that is my displacement at any given time point t. So then we see that let us say we have another problem to be discussed. The next problem is that of a uniform plank which is sitting on a ball. So a uniform plank, a uniform thin rigid plank is placed on top of a rough circular log and can roll without slipping. can roll without slipping. Okay, so we need to show the equilibrium. We need to show that the equilibrium with plank resting symmetrically on top is stable. Okay, so that's the problem here, and let us draw the diagram to see what is the setup. The setup is we have a uniform circular log. So I really want to draw half of the log. The other half we don't care because the plank is sitting on top of the log. So at any given point of time, the plank is rolling. The plank is rolling from the log, right? And so I need to draw. So this is at any given time point t, right? So what are these points? So let us say that the center of mass of the plank is at point G, and we have another point C, which is the contact point of the plank with the log. And now we have that this times this. So we have let's say what have we got? Let us say that the log has a radius a. So let me write down some details. The log radius is a, right? And what we see here is the log radius is a, and we see that the log radius is a, and these are my various geometry here. So theta is the angle that the plank makes with of course with the center of mass subtends with the contact point, and with geometry we can see this particular angle in the diagram is also theta. And now what is happening is when the plank is rolling, its center of mass is also going to get lowered, right? So we have that the plank rolls. When the plank rolls on the log, then the contact point GC from the center, the contact point GC from the center G to the contact point C, which is the arc length of the log traveled, arc length of the plank which is traveled, okay? And we can see that from the arc length formula that this GC is nothing but GC. This is the distance traveled by the plank. This is going to be a times theta, right? So this quantity is a times theta, and now this quantity here which I am marking is a theta times sine theta, right? And we have that this quantity from the center is a cos theta, right? So I'm ready to write down the potential energy of the system. The potential energy of the system will be m times g times the distance traveled by the log, or sorry, the plank from the zero potential. The zero potential could be at the top. See, originally the plank was sitting at the top, happily sitting at the top. We can take that happy position to be at t equal to 0 to be the zero potential or the base position. So we need to subtract the potential which is initially at t equal to 0, and at any given time point the distance traveled by the contact point will be a cos theta plus a theta sine theta, a cos theta plus a theta sine theta minus a. right? And we see that this is my potential. Okay. So, so I can write down the total energy of the system. Remember, the contact point doesn't make. The constraint is that the Planck is constrained to roll on the log, right? So, which means we have, I think, in some of our, I believe in some of our modules, we have already mentioned that the contact point, sorry, the constrained forces do no additional work on the system. So here, due to rolling, there are frictional forces associated at the point of contact, and it is not doing any additional work because there is no sliding. So there is no relative distance traveled by the Planck with respect to the log. And when that happens, there is no additional work done by the contact forces, right? So we are ready to write down the total energy of the system. The total energy being, so what have we said? Let us write down what I just said. The reaction forces are do no work. Why? Because we have that R dot Vc. What is Vc? Vc is the relative velocity of the contact point C with respect to, let's say, the center of mass, right? So Vc, R dot Vc is 0. So the reaction forces do no work. Okay, so the total from energy conservation, we get that the total energy is given by T plus the potential energy. What is the potential energy? The potential energy was mGA cos theta plus a theta sin theta minus 1, right? And now what is my kinetic energy? My kinetic energy will be, well, I can write down, well, what is the problem? What is the problem asking? The problem is asking, show that the equilibria with the Planck resting symmetrically on the top is stable equilibrium, right? So we don't exactly need to find the kinetic energy. Why? Because if you recall some of our previous results in some of our previous modules, we mentioned that the stable equilibria is the one when the potential energy is minimum, right? So all we need to find is the minima of the potential energy, right? So let me call this quantity here as V, the potential energy, and we want to find this minima, or we want to find the extrema of the potential. So V, so dV d theta, we see that this is mGA theta cos theta, and if we take the second derivative and of course we set this equal to 0, we find the value of theta here. We set this, we take the second derivative from here. Of course, from the first statement we see that theta equal to 0 is one possible solution, right? And then when we take the second derivative, we see that this is equal to mGA cos theta minus theta sin theta. And when we plug theta equal to 0, we see that this is mGA, which is greater than 0. So we see from these two statements that theta equal to 0 is the minimum, okay? So what have we found is theta equal to 0 is when the potential energy attains the minima. Let us go back to the diagram. When theta is 0, then we expect that the contact point is at the happy point, which is at the top of the log, right? So when the Planck is resting symmetrically on the top of the log, then we have a stable equilibrium, and that is what we have here on the log. So that is what we have here. That is what we have shown in this problem. Okay. So the next, in our next set of discussion, I want to shift my focus a little bit and talk about the motion of a rigid body and what are the various forms of energy which are associated for a rigid body under motion, right? Where the motion could be that of a rotation as well as that of a translation. So what are we talking about? So let us to begin with talk about the kinetic energy. We have so far talked about the potential energy of a system of particles or the potential energy of a body. So now we will talk about kinetic energy. So kinetic energy of a rigid body about a fixed axis. Kinetic energy of a rigid body about a fixed axis, and we see that the rigid body, now what is exactly a rigid body? A rigid body could be defined as an array of multi-particle systems which are connected to each other with some constraints or fixed constraints, right? So rigid body are rigid array of multi-particle system, array of multi-particle system, and we have that suppose the rigid body B, which is rotating about a fixed axis, a rigid body B which is rotating about a fixed axis. Let us draw the diagram. Let us see what is it. So we have a rigid body which is rotating about a fixed axis, and we see that this is the case. It's rotating about a fixed axis, and we have D, and we have the following Vi, and we have, what have we got? We have, let's say at any given, we can consider any particle. See, rigid body we have defined it to be an array of multi-particle system. So let us call this ith particle to be at position vector Pi, and the body itself is denoted with this letter curly B, and the axis of the particle of the body is this axis CD. Right now, at any given point, the perpendicular distance of the any given particle Pi from the axis of rotation is what matters for the rigid body, right? So let us call this perpendicular distance to be Pi, right? So this is my Pi here, and this particle itself, since the body is rotating, the particle itself will experience a velocity Vi, this Vi, right? Which is the translational velocity of the particle. So let us recap what I just mentioned so far. So a particle Pi moves on the circular path. The particle Pi moves on the circular path as shown here, right? And with radius Pi. So the radius being the perpendicular distance from the axis of rotation, right? So Pi has mass Mi. Pi has mass Mi, and we have the angular velocity about the axis CD being let us say omega, right? Omega. See, omega is the angular velocity of the entire rigid body. So any particle which is on the rigid body will also experience this angular velocity omega. Now omega is the angular velocity. Okay. Now it turns out that the particle Pi, or the particle I which is at a distance Pi, is experiencing a velocity Vi, and Vi is going to be Pi times omega, because the body is rotating, and because of this rotation the particle is at a perpendicular distance Pi. So Pi times omega is the translational velocity of the particle I. So now from here I can write down my kinetic energy of the particle. My kinetic energy, let's say Ki, is going to be half Mi times omega Pi square, right? And from here I can see that I can sum up the total kinetic energy. The total kinetic energy is summation over I, and this is going to be summation I from 1 to n, where 1 to n is the set of all, sum of all particles. So half mi omega I omega pi square, and this is going to be half summation I from 1 to n mi pi square, right, omega square. Okay. So from here I can now notice that I have I have separated this quantity which involves this summation over I over all particles. So this special quantity which is under the sum and which depends on the index I is known as the moment of inertia. So this is going to be half I omega square, where I is the moment of inertia which acts as which has a very similar role as that of a mass of a normal body, right? So moment of inertia of a rigid body, rotating rigid body, is similar to that of a mass of a normal or a let's say a point object which is translating. Okay, so we have introduced the concept of moment of inertia, and remember, moment of inertia is always with regards to the axis of rotation we are talking. If we change the axis of rotation of our body, then we are going to change the moment of inertia. Okay. Well, let us wrap up our discussion by quickly looking at one particular example, a real life example. The example says estimate the rotational kinetic energy. The rotational kinetic energy. By the way, the energy that we just found in this above expression was the rotational kinetic energy, because the rigid body was rotating, right? We could also have the rigid body being translating in some examples later on. So the rotational kinetic energy of the earth, is considered a rigid sphere rotating about a fixed axis through its center. Okay, so what have we got? So what have we got is that the moment of inertia of a rigid sphere, we just write down the formula here. I'm going to tabulate in my next module about the different moment of inertia. But for the time being, the moment of inertia of a rigid sphere about its normal axis, the axis passing through its center, I sphere is 2 by 5 mr square. 2 by 5 mr square, where m is the mass of the cylinder, the mass of the sphere, and r being the radius of the sphere, right? This can be found in standard classical mechanics textbooks, but I will tabulate later on. So the rotational kinetic energy, from here I can find the rotational kinetic energy to be equal to half I sphere times omega square, but I sphere is 2 by 5 mr square, so this is going to be 1 over 5 mr square omega square, where r being the radius of the earth. This is 6400 kilometers, so this is the radius of the earth. And omega, the omega is let me write it here. Omega is coming out to be 7.3 into 10 to the power minus 5 radians per second. These are from standard data of astronomy. And the mass of the earth, capital M or small m, is 6 into 10 to the power 24. So this is in kgs, and this is one astronomical unit. When we plug in all this information, my rotational kinetic energy comes out to be equal to 2.6 into 10 to the power 29 joule. That's a huge number, but typically we write it in terms of astronomical units. But this is, so we wrap up our discussion here, and in the next discussion we will continue our case studies of particles or rigid bodies, this time under constraints, more complicated examples. So thank you so far for listening. Thank you very much.